So it's stuck outside. I live in downstairs. Yeah, yeah. They say the receipt. Yeah.
Yeah.
Okay, yeah, I didn't know that. I'm actually getting some text, we need to send out my number. Yeah.
Can I just try one thing? Are we unmuted on here? Or is it live? Oh,
If you want some.
Right there.
But we are recording, so
Okay, that's good.
something's gonna work. We always get scrappy, and this is the goodness of being in startup culture, right? You always think outside the box. There's a greenfield way of thinking of doing things, and it really drives a lot more than we can ever imagine. So with that, let me quickly give you a little bit of a rundown. We wanted to start with networking. This is really networking. So the more you meet with people, the more you have conversations. That's really the crux of doing these events. We're going to do about an hour worth of talk, 5:30 to 6:30. We're running a little bit behind, but we got a tremendous group of speakers over here. And we're going to start with open table format interoperability with Xtable, where Rahil and Anand are going to take the podium, and we're going to put them on a hot seat. And they're going to talk about the intense work they've been doing in Xtable, which is a really, really important thing. And I'm really looking forward to this talk. The next one is about general model of catalog federation through Polaris. And for that, we have Dennis from Snowflake. And catalog is a very, very hot topic again. So I'm really happy to have Dennis over here talk about what we're doing there. And we're going to close the talks with Iceberg and Delta, collaborating across table formats. And this is Kevin's talk. And we got more chairs. Thank you. No, you're fine. We wanted this. This is a sign of good success. Like if you got fewer chairs, people are standing, outside the gate, trying to get in, like it's like I don't know, like a concert. You want to get in and the concert already started and, you find every way to get in. So, all right, I'm going to pass it on to Matt. Okay, there we go.
Thank you, everyone. Great to have you all here. So great to be part of the Iceberg community. We at Microsoft, my name is Matt Hicks. I'm on the Microsoft OneLink team. Thank you all for coming. We have a few talks lined up for you today, and we're super excited to have you all here. If you haven't had a chance yet, please grab some pizza, and we'll go ahead and pass it on to Rahil from the Apache Xtable and OneHouse team.
Yeah. Hi, everyone. First of all, thank you to the hosts, and thank you, everyone, for coming out. So I'm really excited to be here giving a talk on open table format interoperability with Apache Xtable. So a little bit about myself. Previously, I worked at AWS EMR, where I was on the data lake team, integrating popular table formats like Apache Hoodie, Apache Iceberg with EMR Spark offering. And very recently now, I joined a data startup called OneHouse, where I'm solving problems in the realm of streaming, ingestion, table services, and now Apache Xtable. So before we even talk about Xtable, I do need to cover a couple of building blocks to really explain or give context as to why Xtable even exists and the problem it's trying to solve. So this is just a quick agenda of what we'll be talking about. In terms of questions, I actually will take them after Anand finishes because this is a two-part series. So I'll be talking about Xtable, at least from the open source perspective, and then Anand will be talking about Xtable in production at Microsoft at scale. So I don't know how many people here can relate to the images above, but building a data lake and operating it at scale is very frustrating. It can result in tears. And I find that even for people in the space, the term data lake or data warehouse or lake house, it might sometimes sound a little bit like marketing jargon. So before we even kind of dive a little bit deeper, want to give a little bit clarity as to what these terms mean. So traditionally, a database system basically tied two core entities, that being storage and compute. Computation was primarily done by taking SQL, transpiling that into some optimized plan that would then scan the actual data that sat within the local disk of that compute node. And these systems had very mature features in terms of cataloging, which essentially is mapping out maybe a collection of files to some table identifier, things such as resource management, access control, etc. So they were a very robust product, but the main biggest issue for users was when I wanted to scale, let's say, compute and storage independent of one another, you couldn't do this in this kind of architecture, and it became very expensive. Then another architectural pattern came out in the early 2000s with the Hadoop ecosystem. So Essentially, data lakes became synonymous with taking open files, something like Parquet or text files, and just dumping it on a distributed file system, something like HDFS, and eventually it became cloud storage like S3. But I think the biggest issue with the data lake was that it was ahead of its time, and it didn't have a lot of core database guarantees that we got with traditional systems. So things such as taking your collection of files and having some aspect of atomicity, things such as being able to perform table maintenance. So as your files grow in size, are there operations to clean out, those files after a certain period of time? So the current architecture today now is a mix of these two paradigms, both the warehouse and the lake, which is now this term lakehouse. Essentially, it is an unbundling of the database system. So today, users can choose their compute engine, whether that be something like Apache Spark, Apache Flink in open source, or they can use a vendor solution like Microsoft Fabric or AWS EMR. You can choose the ways in which your data is actually serialized in some open file format, something like Apache Parquet or Apache Avro. And you can choose the actual service in which where you want to store these files, something like S3 or Google Cloud Storage, Azure Data Lake Storage, etc. But the focus of this talk is primarily focused on the middleman, essentially these table formats that sit between the compute engine and storage, and the guarantees they give in terms of being able to support transactions. So at the core, these table format projects, I think this audience is pretty familiar with Iceberg, but at least for like Hoodie and Delta, they all have these metadata files that sit on top of your actual data files. And these metadata files are essentially adding asset transactions to the data lake. So what I mean by this is being able to support atomic writes. So when I do a write to my table, is this an all or nothing operation? Supporting things like concurrency control. Say I have two writers writing to my table. Do I employ certain strategies for maybe locking on the table? Do I employ a strategy like doing optimistic concurrency, where I fail one writer and ask it to retry and fetch the latest state of the table? Supporting things like time travel queries. So as I'm making changes to my table, maybe I care about the specific state of the table at a certain period of time. Things such as giving the engine maybe statistics in terms of column statistics or partition statistics, so that my engine can actually fetch the files only relevant to the query. There's a lot of features, but I can't really go into all of them. But I think the core thing I want to really emphasize is that if you were to look at these table format projects, let's just say you want to create a Hoodie table, a Delta Lake table, or an Iceberg table in some cloud storage like S3, it really is just these metadata files that are sitting on top of your data files. And usually the standard in the industry now has become, at least for data files, Parquet. And each of these projects have, their own unique way of representing this metadata. So as you all probably know, for Iceberg, it's a tree-like structure where you have a list of snapshots, each snapshot referring to a list of manifest files, each manifest file referring to a list of data files for what was added or deleted in that operation. For Hoodie, it's a notion of basically a timeline, where as you're making commits, there's a notion of a file group, and a file group is nothing but just a collection of these file slices that have a reference to a Parquet file and a log file for the actual appends. And Delta Lake has a notion of a transaction log, which is just basically a sequence of these JSON files. I think there's also a notion of checkpoints that kind of aggregate these JSON files over time so that you don't have to read a bunch of small JSON files. So I won't go into all these examples because I think that also would take a lot of time. So let me leave you with one at least. Say you're a data enterprise and you have data engineers and they're using Apache Hoodie because they've heard of its great capabilities when it comes to ingestion and streaming. But in that same organization, you have your analysts and they want to use something like Snowflake because it has a very good use case for business insights and reporting. But Snowflake is very much supporting, or at least, integrating very well with Iceberg. And you want your analysts and your engineers to have the same view of the data. And even to add on to that, you have your data scientists, and they enjoy using the experience of maybe Databricks' notebooks with engine like Photon because it supports very fast reads with Delta Lake. So if there was a way for us to essentially mix and match formats without having to actually copy the underlying data files, but just keep track of metadata, between them, it would open a lot of use cases in terms of the engines you can actually bring to your data. So essentially the solution is Apache Xtable. So to clarify, Xtable isn't just another table format. It is a omnidirectional converter that handles the job of basically converting metadata between each of these table format projects, whether it be Hoodie, Delta, or Iceberg. So just a quick timeline of events for how Xtable came to be. Essentially, the company I work at, OneHouse, had made an internal product known as OneTable. We did a co-launch with Microsoft and Google to have this open source, and then more vendors and companies got interested in the project. So we were able to donate this to the Apache Software Foundation. And I think the big news last year was Microsoft Fabric and Snowflake had a partnership. So essentially, there's a product in Microsoft known as OneLake, and under the hood, it's using Xtable to handle the conversion between Delta Lake to Iceberg. So I'm really excited for Anand's talk because he'll be speaking about how they're using OneLake and Xtable at scale at enterprise level. So you might be asking though, how do you as a user go and actually interact or use Xtable? Essentially, you'll construct a YAML file, and this YAML file has three core things. So the first being, what is the actual source format that you're currently working with? What is the target format, or basically the thing you want to convert to? And then finally, usually a cloud storage path to where your table is located. And if, for example, let's just say I had this hoodie table over here, I can then download the Xtable utilities bundle jar, pass that YAML file that I created, and essentially I can run this Xtable jar either on my local machine or on a remote cluster, but it will handle the job of creating metadata for not only just, obviously Hoodie was already there, but Delta and for Iceberg. And the benefit of that is now I haven't gone through any complicated migration process of recreating data files or recreating tables. All I've done is just created metadata, and essentially I can bring an engine, something like Apache Spark, and be able to interact with that same data with all these formats, as you can see with Spark.readup format. So now we'll be looking a little bit at the internals. This slide, I think, has a lot of information on it. So the following slides will be looking at individual slices of how this conversion happens. So the three core components are, there's a conversion source, a conversion target, and a controller that orchestrates the entire process. So a conversion source is nothing but essentially breaking down what a table format is into like building blocks. So each format has a way of representing things like schemas, which is basically the structure or the types of your table. Things such as partitions, which is the way in which that table format is actually distributing data on storage. Things like we talked about a little bit earlier, column stats or partition stats. The actual pointer to how it's representing a data file. So maybe some path on storage to where that file is located, as well as what file format it's in. And then commit extractor is nothing but, Iceberg has a notion of a snapshot, but he had the commit. In Delta, there's a transaction JSON. So being able to extract the actual operation that happened on the table. And what I really want to leave you here with is that this is a very easy, extensible interface so that in the future, other table format projects outside of the big three can go and extend this interface so that then they can also interop between Hoodie, Iceberg, and Delta. The conversion target is nothing but just a mirror of source, but instead of reading, now you're writing to your target format. So essentially, you'll also go and implement this interface and then, similar to what I mentioned before, write out how that table format represents its schema, partition, stats, etc. And finally, is the kind of the brain of how Xtable works is this conversion controller. So this is basically handling the entire sync process. It handles things such as obviously taking in the user's configurations, initializing each of the table format clients, but it also handles things such as state recovery. So say I'm running the sync and I have like, let's just say 5 commits from Hoodie and there's a network failure. I should be able to keep track of what was the last sync instant and then be able to pick up from that point and continue on in my metadata conversion. Also, it has modes for doing a full sync or incremental sync. So say I've already synced 5 commits in my table, and now 3 new commits come. I don't want to have to look at the entire timeline of events. I should just look at what's changed between them. So the biggest question we sometimes get at OneHouse is why build something like Xtable? So for OneHouse, we're interested in building what's known as a universal data lakehouse. We want to be able to consume from many types of data sources, whether that be database logs, Kafka streams, or even just raw Parquet files sitting on S3. So we have a high quality, very fast ingestion product, and then we allow users to specify what is the storage format they want to use, whether that be Iceberg, Delta, Hoodie. And the benefit of that is now that it's in one of these open formats, it opens a bunch of use cases for the actual engines you can bring. So you can use Snowflake with Iceberg for BM reporting. You can use ML, you can use Databricks' engines for ML and AI use cases. You can use something like Flink with Hoodie for streaming. And we handle the hard job of at least optimizing your tables. So running table services like compacting your data files so that they're better for query performance, things such as cleaning and archival so that as this metadata grows, you can start to expire or remove it after a certain threshold. And also low-code pipelines. So building a data lake is very expensive because you have to hire a bunch of engineers, each of them familiar with a particular ecosystem, and usually have to stitch together a bunch of PySpark or Scala scripts. But in our product, we ideally want it to be as easy as possible for people to build data lakes or lake houses, say. So in terms of the roadmap, we already have the major projects supported in terms of Hoodie, Iceberg, and Delta, and we test this out with a couple of popular open source and vendor engines. I think the way in which the industry is moving now has been very much in the catalog space. So we believe, at least at OneHouse, that there won't be even one catalog where all the data will be essentially interfaced in. We want to be able to sync your Iceberg, Hoodie, or Delta tables across many different catalogs. So say I'm using something like Hive Metastore, and I want to have those same databases and tables reflected in something like Glue or Lake Formation. So we've already implemented this, but we're looking to add more catalog support, so things in the Snowflake and Databricks ecosystem. And similarly, once you've synced your catalog resources, the next big question is how do you actually enforce governance? So each of these catalogs has their own unique way of representing permissions. So things such as being able to grant a particular role or user the ability to do maybe a select query, so only having read access, or maybe only letting some people have the ability to write in terms of granting them an insert or update permission. So there's an RFC right now that anyone can go and actually read to see how we're trying to map out this internal model. Final thing I'll talk about very just briefly is just merge on read. So these table formats have two core concepts. One, which is copy on write. Essentially, when you make a change, you will basically version or recreate a Parquet file. But the merge on read concept is essentially, it's very expensive to keep recreating these Parquet files. So rather, let's keep the actual appends, like let's say delete, for example, in an auxiliary file. So for Hoodie, there is a log file, which is Avro based. For Iceberg, at least in the V2 spec, it was positional deletes, which would basically be an additional file, a delete file, which would keep track of the ordinal as well as the file path, so that you can at read time be able to stitch together if this record is actually needed or not. So being able to now convert these additional log or delete files is the next step, since you already have copy on write supported. And then eventually also adding support for other table format projects. So yeah, we really are looking for people to come and join the community. And these are the current contributors across many different organizations, OneHouse, Microsoft, Snowflake, etc. So, a big thanks to all the people across the industry that have currently contributed to Xtable. And then special thanks to Kyle Weller and Deepankar for helping out, with this talk. So thank you, everyone. I'll be passing now to Anand for the second part of this talk.
While we get that, I'm Anand. I'm from the OneLake team in Microsoft. It's just great to see you all here. And I think welcome again on behalf of Microsoft. It's exciting to be part of this community and hosting this event.
I just want to see if we can get PowerPoint up.
Okay.
Oh, it's gonna go to the whole entire.
Right.
Okay,
there you go.
PowerPoint right there.
Can you just present? I know, but I need to share. You stop sharing. Or is it still sharing? Not yet, I think. Where is it actually going?
Oh, we have to go back on.
Okay, I just. You there?
Technical report is very hard for software engineers. This is probably the hardest part of the talk, to be honest.
You're good now.
It's good? Okay.
Okay, there you go. Great. Okay, so I'll start now, family. Rahil talked about Xtable, what it does. It's a great way of transforming between metadata formats because data is the same, is you just want to use it in a different way. And now I'm going to talk about what OneLake does. So we use Xtable. In fact, we also contributed to Xtable. And it is better. Okay. So what we want to do, again, is emphasize this interoperability, right? We want to have the ability to let our customers have the flexibility to choose whatever engines they want, whatever is best for the job that they want to use it for. And we don't want to have engines, analytics engines, to have to worry about which format they're working with, right? Now, in the real world, this data is somewhere, right? And we have to somehow get access to the data, have to show it up in the right form, and make this whole business of transforming, etc., seamless. So, okay, here's just an example of what we want to do. There is an iceberg table, table A, lying around or floating around somewhere. We have Microsoft Fabric, wants to read this data, and then analyze it. We do something with it and transform it and then create another table. Fabric works with Delta, so it writes down a Delta table, that's table B. And then we have Snowflake. Snowflake wants to read the data in Iceberg form again. Right? So we really want to build these flows where the engines are agnostic of what the original form of the data is. So now we come to OneLake. OneLake is our SaaS data lake for entire organizations. So just like OneDrive is for documents, OneLake is for data, right? And the job is to abstract away the entire data layer. Right? You talk to OneLake, data can be there or data can be somewhere else, and you can bring in data through shortcuts. We'll talk a little bit about that. But originally, OneLake started with the Delta Lake format, right? And now we're adding Iceberg format. Okay. So here's a view showing some data lying in some storage. Where is it? It could be in a lot of places. Could be in OneLake itself, could be in Azure, could be in S3, GCS. That also doesn't matter, right? You can see that there's an iceberg table, you have a data, and then you have metadata. Metadata has the metadata JSON files, arrow files, etc. How do we bring this into OneLake? We create a shortcut in OneLake, which just points to the iceberg table, right? Important to note, the data is not being copied, nothing's being copied, but you have a way to access that data from within OneLake. The extra thing we want to do now is to add another layer here, because the original data was in iceberg format. We convert it, it becomes Delta. Anyone who accesses this table through this shortcut should be able to consume it in either format. Okay, so what all do we have to do? How do we get this done, right? OneLake is the abstraction layer, so it has to know where each piece of data is. It doesn't matter where it is, as long as OneLake knows. It has to understand metadata formats, and based on who's asking for what kind of metadata, it has to convert it.
So here's some table in Iceberg format. It's in one lake. Somebody's asking for it. Some Microsoft Fabric engine is asking for it, but they're asking for the delta log, right? Because that engine only can read delta. So what do? We detect that it's an Iceberg table, convert it. This is where we use xtable to convert the data, and then send back the new log. It's another important thing here is the original table, this Iceberg table that we saw, we might not own it inside one lake, right? So it is somewhere. We don't modify the original location, right? We built this whole abstraction layer of building a delta log is on top of that, and it's transparent to users. Now, in any real system, live system that is scalable and enterprise level, there will always be trade-offs, right? So here are the kinds of things we need to think about to actually build a real system. There is consistency. Do you want to, every time somebody asks for data, do you want to give them the exact same data in both formats? Or is it okay to be a little lax about it? How fast do requests need to be? Generally, in a real system, you want requests to be pretty quick, right? And optimize for that. We could be highly efficient and do things only when they are required to be done and not do anything extra. Or we could do things which are not required, but might be required in the future, just anticipating, right? So there's a scale there. And then all of this usually has to be done at high scale. So this is just the kind of things we had to think about. And I'll show you an example of what kind of, how to slide the scale, and then what does that mean? For example, if you want it to be highly consistent, but also efficient at high scale, then maybe you can be mostly consistent, which means that you can allow a little bit of staleness, but not too much, right? We have to scale this horizontally. There'll be lots of different engines, lots of different clients asking for the same data or different data lying all across in different storage. And so this is where the work comes in to take something like xtable and then scale it out. And here we have to be, it has to be stateless. It has to be, there are several things, assumptions that you might get away with if you're running it on a desktop that you can't do anymore. And then finally, if you have, when do you want to convert, right? Do you convert every time somebody asks for the data, or do you keep it converted whenever something's written? And can you do that or not? For example, if we convert every time somebody writes to it and nobody's asking for this, then we do a lot of work where it might not be required, right? So that's the difference between make on read and convert on write. This is kind of similar to what Rahil talked about in case of merge on read and copy on write, something similar. Okay, there are many challenges. I'll just point out one. More things that we have to do or we have to think about. One of them is the portability of Iceberg files, right? Iceberg uses absolute paths inside the metadata. This means that if we point to something from a shortcut, the metadata files in the region where the grayed out part is actually referring to the data not through the one lake shortcut, but it's directly there, right? So it still can't be used directly. It's something that we need to solve. Okay, so all that was talk. Now time for some demos. This is actually working in production. The first thing we do is we want to go to Snowflake and have Snowflake write some data in Iceberg format. So all this is just getting a path from one lake and putting it into Snowflake so that Snowflake knows where to write the data to. We're creating a table. This table will be written into one lake. Okay, it's done. Then we add some data to the table. And then we go back to one lake. Going to one lake, this is in the files section. This is just a restriction for now, because you created in the file section. The table section is structured data, right? But in the file section, you see that you can see everything that Snowflake created, so the Iceberg metadata. Going back, now you create a shortcut. shortcuts can be to many places, but in this case, it's inside one lake, right? And you go to where do you want to create the shortcut to? That's where the Snowflake data exists. So we create a shortcut there. And okay, so here's the part. Now we see a table here, right? This table, whatever we are presenting here is reading it in delta format. So it's already used the original place. It used X table, converted the data, and now you can see it in delta format. Okay, we can run some queries on this in Fabric right now, right? And it should all work. It refers to the original data. There's no data movement. We are not also adding the generated data log in the original place, but to the engine who's asking for this data, it all works, right? It all seems like it's a delta table. Okay. Again, accessing it through one lake, we get the table. We can also generate Power BI reports using the same thing in Fabric. Anything that you can do in Fabric with a delta table, you can do this with this table, which was originally created in Iceberg format, right? Now we go back to Snowflake and try modifying some data. So we're adding a lot of files. What happens? Then we should go back to one lake. And once it's done, you'll see that the updates are now visible in one lake. Okay. Refresh the data, see the new data. There you go. So behind the scenes, it's looking at what is the latest data available in the Snowflake, in the Iceberg format, getting the equivalent, running the X table, all that. This is just to show that shortcuts can be created to many different places, right? We talked about S3, Google, OneLake, etc. And this is an example to show something in S3. So there's data in S3. We create a shortcut in OneLake to that data. The same thing, nothing changes. If you access it through OneLake, it still seems like the data is here. You can see it and can load it up. Okay. If you view the files here, again, you see the delta log, right? But if you go back to S3, there's no delta log there. It's just the original format. It's an extra layer that we add on top. And I think that is it. Thank you.
Any questions from the audience for me or Anna?
Regarding the one table, if you want to update the one table, and choose the format to update data back into. For example, if I wanted to update the data range from Iceberg data format.
So can you repeat the question? Actually, I can repeat your question as I understand it. Let me see if I got it. So you have
The source format is different.
yes.
The target format,
Yeah.
I wanted to choose a particular format.
Right. So we don't do that right now. One of the restrictions right now is that there is an authoritative format, right? So the original table was written in Iceberg. When we show it up in one way, you can access it as data, but you can't write to that, right? Right. Right.
Catalog position or storage level metadata.
So again, right now, it is relying on the file. Oh, yeah. So does it depend on a catalog or how is it finding out where the data is and what's the latest version, like that, right? Okay, so it's looking at the file system, uses the file system as a catalog, and it knows how to read, what's the latest version that's using that. That's right. There's a lot more to talk about catalog, so I'm sure we'll talk about it.
You know, we have a lot of papers. We have papers, we want to make a time.
So I think for just partial files, it's pretty easy because essentially most of these table formats have a very simple, very similar strategy for versioning or making changes when it comes to copy and write. So I think the big challenge now is how like Iceberg, especially now with I guess the V3 spec, Delta and Iceberg are aligning on I think these vectors that are more closely to Delta, yeah, more good now. So that concept is a little different than hoodie representation, right? For this agro-based log file where you're constantly appending your transaction. So I think merge on read, there's already an RFC out. I think a couple of people from one out Microsoft have put out a proposal for how we can, do the conversion for this additional merge on read use case. But yeah, I think copyright is fully supported. And another challenge I think will be just knowing when to sync the actual, because you're writing, these commits. So you want to make sure that you're not having other operations maybe happening on a table when you do the thing. So I think one out we have a service that handles this for you, intelligently decide when to do this thing or not. But for the Excel product right now, it's more ad hoc, which we are in the future probably thinking about building a more of a service off for this, so that users don't have to think about this. But hopefully that answers something that your question. Thank you. Schema evolution? You're saying is schema evolution supported?
Yes.
So schema evolution is, supported in all of the table format projects. So what we're doing is just converting between, table format projects. And since that is just a property of, each of them, it is supported. Support.
Iceberg, there is a functionality where you can create dynamic partitions, right? Using the functions of the function. It will not also be retained when you change the basic format.
I honestly will not, I don't have that granular level for at least the dynamic partition case, so, okay, so it looks like my head of product is telling me no, so, yeah, currently not supported. Okay. If no more questions, then we'll give it to Dennis, who will be speaking on catalog federation and Polaris.
Right. Thank you very much. And I think, there will be good synergy. And people were asking about the semantics of conversions in the context of catalog federation. And actually, it works well together. So that's an excellent segue. So I'm Dennis Wu. I'm a software engineer at Snowflake. I've been working on catalog federation in Apache Polaris. Apache Polaris is an open source implementation of Iceberg REST catalog with productionization in mind, and which supports things like RBAC and caching policies, things like that. So for this presentation, we'll be going through an overview of what federation is. Even if you're just coming in not knowing anything about federation, we'll talk a little bit about that. We'll talk about some generalized concepts that we want to apply more broadly, even beyond necessarily the Polaris Catalog Federation project, but which are applicable to other similar scenarios. And then we'll sort of deep dive into the anatomy of how this works in Polaris, the current state of things, what we have and how we're thinking, and then we'll do a demo. So to overview catalog federation, the most basic formulation of federation is simply that your catalog, your local catalog, can serve as a pane of glass into any other remote catalog. So a very simple concept at its core. Where it gets interesting is when we have things like different implementations of catalogs, different flavors of remote catalogs, different formats even, right? So when we start talking about combining format conversions along with request conversions and request transformations where a remote catalog might not speak the same language as your local catalog, for example, but then you'll want to have client libraries which can, again, go through that single pane of glass and not have to know whether they're talking to a remote catalog or a local catalog. They don't have to know, different protocols. They can just talk to one place. And in particular, if other catalogs don't serve the same set of features, then a federation layer is an opportunity to add in those kinds of things like authentication, authorization, caching, and other features like that. And one thing we also notice is there's
a really broad range of use cases for federation. So often when people start talking about federation, they're actually talking about a lot of semi-related potential use cases. And sometimes this gets lost when we use only, you know, just terminology that talks about things in terms of generalized federation. But there's really a lot of related concepts. And, you know, we've seen use cases where, for example, federation is a solution to being able to unify your data lakes that have organically grown with lots of, you know, disparate projects, right? Like things, projects pop up, acquisitions happen, skunkworks projects, you know, turn from maybe like an intern project into something that lands itself in production. And this is something that always happens, you know, this is something that really identifies the data lake historical you know, DNA really of the data lake, right? Things pop up, and you have all these organically grown catalogs, and you know, organically grown groceries might be healthy, but you know, not so healthy for your data lake, right? So you know, federation would be a way to bring a little bit of order to that. We also see it come up in peripherally related use cases related to failover, for example, replication. When we talk about tooling that can create copies, read-only copies maybe of catalogs or backup copies, often things that start looking a lot like federation also come into play. In some cases, people just want to migrate off some legacy Hive catalog. Sometimes you want to add some functionality on top of these legacy catalogs. Maybe for the long term, maybe you're not migrating, but you still need to slap some RBAC layer on top of that and things like that. So that's part of why we want to talk about a very general model initially, right? You know, regardless of what we're trying to tackle initially in Apache Polaris, we want to have sort of a generalized model where we can at least reason about constructs in a common terminology. So, you know, first, one of the things we'll talk about is this idea of just-in-time actions, which, you know, I'm sure it's not a completely new concept, but in this case, you know, we're talking about in a situation where a local catalog might have functionality which depends on a certain amount, certain prerequisite local state, or certain assumptions about local state. The idea being that with just-in-time actions, like just-in-time creation, we want to take away the burden from the user of having to think about setting up that local state preemptively and just seeing how far can we go by deducing the prerequisite local state without that intervention. And in this way, we can have things that feel like really hands-off federation, and yet we can still get the benefits of features that might need local state. And I know that this might sound kind of abstract. That's by design. You know, as we go into the demo, we'll see like how that applies concretely to actual features. Similarly, with just-in-time refresh, you know, if there's an implication that there's some amount of local state that is sort of functional, that is stateful, that represents that remote state, to be able to define what it means to efficiently be able to refresh that just in time, you know, as we're serving the request, but again, you know, without that user intervention. So another thing that we've seen is just introducing some amount of terminology, some of which may or may not already be standard, but at least the concepts we see popping up time and again is, you know, we'll say, if we're talking about a catalog being the source of truth for something, that means that that catalog that we're talking about is just the primary source of truth. You know, it's pretty straightforward. It holds, you know, the state of the world for that entity. And generally that means that's also what's responsible for coordinating updates, like coordinating transactions, commits, things like that. This idea of a facade is how we'll refer to entity representations in a local catalog that in some way reference that remote source of truth. So it could be a pointer to a remote source of truth. In some cases, that might be indeterminate as well. So like in the case of a static facade, so we have these two subtypes, static facade and pass-through facade. In a static facade, there's this idea where we might say, we might have a pointer that says that this piece of, like this table, for this iceberg table, is externally owned. But we may or may not actually talk to that external owner. in this case, it's still, we see it as being related to federation in that even if that's abstract, this facade exists to have an abstract representation of that remote entity. So oftentimes we'll see this come up, for example, when you're talking about linking in an external table. So when you create an external table, at least, like let's say a traditional Hive external table, and it's read-only, what you're kind of saying is like, I just want to, you're stating that you have an entity, you have a facade, where you want this to be able to function by itself in Hive. You want to be able to read it. But you want to say, look, something else actually owns this. So don't screw around with it. Don't try to clean up orphan files. Don't try to accept updates or anything like that. And there's a couple other patterns we'll see that reflect this. In a pass-through facade, the idea would be we still want to have a local representation of this entity. But there's a pointer to that external source of truth that is always reflects the up-to-date state. So whenever we're serving a request, like loading a table, and let's say we have a pass-through facade, that means we do want to still load the table from the remote source. But we are going to store enough, we would still do have a facade in this case, right? We still have some entity representation. And this is somewhere in between the idea of just proxying requests through versus having something that functions by itself. And we'll see how that might that applies to things like migration scenarios, or even without migration, you might want to perform caching. So you could say like you have a pass-through facade, but you define some protocol where you can cache things and efficiently determine whether or not you need to do a just-in-time refresh. Finally, in the case of having an implicit entity, that just means that there won't be any local representation of that entity at all. Your requests are all passed through to the remote catalog, and you discover that entity at request serving time. So it's interesting that even outside of the world of Iceberg and Federation, we could compare, as an analogy, pass-through facades might feel like a file system symlink, right? You've created a symlink that points at a remote source of truth. So there exists an inode there that represents your symlink, and yet the contents are actually defined by the actual file. In an implicit case, when you mount an NFS directory, for example, you're not immediately sucking in all the inodes from the remote source. But as you try to access a file, you'll make those network calls to get the files. So now let's jump into a little bit more specifics. I know that was a little abstract. So looking at the anatomy of what it means to handle a catalog request. So some of this is a little specific to Polaris, but also I'm trying to use somewhat generalized terminology here. So at a high level, what does Polaris does? It's really just these four things. Polaris will figure out what are the identities and roles coming in with the request. It will figure out what are the securables that pertain to the request. It'll make a decision, an access control decision, to say yes or no, whether this thing is allowed. And then it'll execute the business logic, right? So just those four things: get the identities, get the securables, make an access control decision, and then do the thing. Like I mentioned, right, we want a general model that talks about all these different things in terms of federation, even if typically we break out federation to an identity provider is typically a different thing from identity from federation to catalog contents, and yet they are tightly they are closely intertwined. So we'll sort of talk about how this pertains to all of those together. In Polaris specifically, there's sort of this upper layer. The upper layer principals, principal roles, and catalog roles form the foundation of that identity and role system and hierarchical roles. At the bottom, we have catalogs, namespaces, tables, views. These are the Iceberg objects. We call these securables. And then in Polaris, the authorization policies are expressed as grants. So any of these links that you see in this graph that both are grants between from a role to a higher level role, or a role to a principal. Those are grants just the same as grants for privileges on securables are to the catalog roles. So we have grants, we have these things, and the way that those four steps that I talked about happens is depicted here. There's an algorithm within Polaris where it'll fully resolve those identities and roles. It'll fully resolve the securables, and then it performs a big crunch to determine the authorization decision. And this is where, it can get a little complicated with fine-grained privileges, but in the end, that's all it is. So let's see how that might apply to the model. So we introduced terminology, right? We talked about sources of truth, facades, and then we talked about these this hierarchy of identities, hierarchies of securables. So essentially what we can do is lay out all those things that we just listed. At the top, we have principles, we have identity, we have roles. At the bottom, we have these securables. And then let's unroll it. Let's say, like, where is the source of truth? Where's the facade, and what kind of facade? So today, in Polaris already, or from early on, since the invention of Polaris, Polaris had this API called send notification. And the idea here was that even in the absence of pass-through federation, that there would be this idea of federation based on static facades. So we see that in this world, you would explicitly create a catalog, a so-called external catalog to contain your entities. You'd create a namespace, and then you'd use the send notification API to essentially tell Polaris, look, there's a table. It's a remote source of truth, but we won't actually care about that remote source. We'll basically say from the outside, something else, some other tool, some other managed service, will be able to send notifications to tell that static facade when things have changed. And then those static facades can survive on their own to serve requests. So this is sort of the most basic getting started way of doing federation, because it's kind of a catch-all. If nothing else, you can always write your own tool that pushes in state updates. But it's not very user-friendly because you have to have a tool that pushes those state updates. On the other end of the spectrum, you can imagine extending this model to include like a world where, let's say, everything is federated in different ways. So you could have all your identities and even your roles synced to something like Okta or Entra. So you could say that we build a system where principals and principal roles come from your third-party identity provider, maybe defined with just-in-time creation of pass-through facades. You could say that your authorization engine is also remote. It could be something like Apache Ranger. And then your actual securables, your catalogs, your tables, your namespaces might actually be defined in a remote Iceberg catalog. And this should all be able to work together long-term, right? You should be able to mix and match any kind of federation under this model. So for now, we are going to just define somewhere where we can get started, but something that adds a lot of value in Apache Polaris. And there's more details in the associated proposal document, but what we're basically working towards is to say that we'll have pass-through facades that are just-in-time created for namespaces and tables. You define a catalog level static facade first, and then everything else is just pass-through and just automatically works. So what this means is the user experience will be that you create a catalog, you say that it's a federated catalog, pointing out a remote. The just-in-time creation sort of gives you the best of both worlds. By creating the entities just in time, we can preserve the existing machinery that performs RBAC, that performs that authorization model. It's also a useful building block towards things like caching functionality or catalog migration scenarios. But because it's just-in-time creation, it has the same ease of use as implicit federation, meaning the user never has to juggle with tables or namespaces or anything. You just link in your catalog and everything should just work. For the MVP, we are going to define, this might be more of a technical nuance, but essentially you would define a connection in terms of a credential, an identity. For now, to get started, you would define your connection configuration with like a system identity that behaves as essentially a super user role into your remote catalog. And then what this allows us to do is to have Apache Polaris still provide its own RBAC system for the principles defined in Polaris, while the federation connection happens as a system identity. So We'll do a demo. I think, and we'll take questions afterwards. I think it's possible the demo will also help answer any questions. So let's do that. I don't know if there's probably, let's take this microphone here. Okay. So, okay, I'll try to make sure you can still hear me. Okay. So to begin with, what we have here is I have Snowflake Open Catalog, which happens to be a managed Iceberg REST catalog. It also happens to be based on Polaris, but as far as our federation is concerned, we don't really care about that. So we have Open Catalog. We have some data already in there. I have S3 open over here on the left-hand side, just so we can look at the files as they come. What we're going to do is we're going to run a local Polaris server. So, let's see. So this is all open source. This is also work in progress, but technically anybody can go and git clone and check out my branch and do this yourself as well. So initially, we'll say before we run a local server, let's try to talk to a local server that doesn't exist. So let's say, oops, okay, we're gonna run Polaris command line tool. We're going to use local secrets. So root secret, this is a development credential. So we'll see, like, since I'm running a local development server on local host, we're just going to use development credentials. And right now, since I'm not running any server, we see that the connection failed to connect. And that's expected, right? So this means there's no tricks up my sleeve. It's already, there's no local server yet. So we're coming from a completely fresh, clean slate. So now I'm just going to Gradle run just to start the server. And as soon as we see the iceberg scroll by, okay, I think it scrolled by really quickly there. So the iceberg scrolled by, there's some ASCII, we can take a look at it. So the iceberg means that it's ready to go. So don't worry about the 97%. If you see the ASCII art, you're good to go. So now let's rerun that command we just did. So sure enough, we see there's no catalogs yet, but we also didn't see any error. So that's good. We talked to our local, we managed to talk to our local server. So now we're going to create that catalog facade. So as we see here, the way this works is we're again talking to our local server. We're going to provide a storage configuration. We're going to give it an S3 path. And here we're going to tell it a remote URI. So this is the magic where we tell it, look, this catalog that we're about to create, this instance of a catalog we're going to create, points at this Snowflake Open Catalog. And in there, as you can see, I have my secrets hidden. So we're going to pass in the secrets, and then Polaris will securely store those secrets. Those are the system credentials I talked about that know how to connect to the remote catalog. Now, sorry, I'll just do this again. So let's list the catalogs again. Now we see that we've created an external catalog. You can see how our client secret, client ID are hidden. So they're safely stored securely in Polaris. And we know that in this catalog, it knows to connect to that remote connection, snowflakecomputing.com. Now, let's do some things. So right now, we haven't created a principal yet. We haven't done any RBAC types of things, but as root, we can at least list the namespaces. So we can see that even though we just started a fresh catalog, which would normally be completely empty, when we list the namespaces, and as we do that, we can see how things scroll by in our local server. So it is going to our local server and relaying over to the remote catalog. We see these pre-existing namespaces. So that's good. We already see things that already exist. Now let's create a brand new principal. So here we just used the command line tool to create a new principal, and now we're going to use this principal, which we called Spark Worker. We're going to use it to try to list namespaces. Oh, so we see we're forbidden. We're not allowed to list namespaces. Why is that? It's because we just created it. There's no permissions assigned granted to it yet. So as expected, we can't even list namespaces. Similarly, we can't call get on the namespace either. So now we will fast forward a little bit. You don't need to go through all the RBAC mechanics, but we're going to grant privileges. We're going to create privilege, principal roles, catalog roles, etc. And we're just going to go ahead and grant some privileges to this principal. So so far we've granted everything up to namespace list. So if we list the privileges for this principal, we'll see that, yes, the Spark worker now has namespace list. That means that if we list namespaces, it should succeed, and if we get namespaces, it should fail. So the first one succeeded, it listed namespaces, but then we also see, oh, we don't have load namespace metadata, so it'll still fail. Now, so since we're just doing a demo, so we don't need to worry too much about permissions. So let's just YOLO this and give the big permission, catalog manage content. Now this principal can do everything that we want it to do inside of that catalog. Now we're going to load up Spark. So here we have that Spark credential that we got when we created the principal. We're going to make Spark talk to the local host catalog. And this is Spark just out of the box, right? So this is the Iceberg REST API. There's no special client libraries needed for Polaris. And we're going to spin up a Spark SQL shell. Okay, so now that we're in Spark, we can show namespaces. Sure enough, we should see the pre-existing namespaces. We can create namespace Redmond Meetup, let's say. Okay, so now that we've created that namespace, let's see if it shows up. I refresh, and sure enough, it shows up here. Let's use that namespace Redmond Meetup. Let's create table 1. We'll have a string. And again, let's refresh. And sure enough, that table 1 shows up. If we open this up, we see that call 1 that we just created. And let's refresh S3 now. So let's open. Oh no. Well, okay. Let's try this. Okay. So Redmond Meetup, table 1, metadata. Great, there's metadata available. Let's insert into table 1 values, right? Hello, Iceberg Meetup. So with federation, this also allows Polaris to perform credential vending. So that's one of the key features of Polaris. It can vend credentials for at a table level, level of scoping of the credentials, so that client libraries don't need to have latent credentials available. So we can select. Hello, Iceberg Meetup. Great. And now if again, let's refresh S3 and we see that, there's new manifest files. If we go into data, we can see that our precious hello Redmond Meetup is stored safely in Parquet. Now, if we want to drop, we can drop table 1, purge. And, go back up to Duho catalog. And sure enough, there's no more, our data is safely scrubbed out. And we can also drop the namespace just for completeness. Okay, so we cleaned up after ourselves, we go back to our catalog and we're ready to run the demo again if we want. So that concludes the demo. Any questions?
So I'm trying to understand, we have a principal role and then we have a catalog role. So what is the principal role then basically containing? Is it just pointers to like the access it has on this catalog only?
Yeah, so the two level, this is a little bit, outside the scope of the Federation topic, but in Apache Polaris, principal rules generally feel a little bit more like functional groups, or like let's say business groups. So like maybe you have like developers in your company, and you have managers or finance managers. And then this multiplexes down into catalog roles, which are more convenient to do by sort of data, like physical functions. So you might have sort of like, you'll have like server logs or server logs processor, right? And then that way you have that layer of indirection. Yeah.
Right now, if I understand correctly, right now, the catalog owners have to publish it in in Polaris, right? The tables and catalogs and this. Is there any option to mirror it? So I go and say this is my catalog, and Polaris goes and pulls all the information. Is this possible?
Yeah, that is so like I meant when I said that the existing Polaris, so that's before all this federation work, right? Like without the work in that branch I just demoed, you would have to push data into Polaris. The what I just demoed actually shows that nothing had to be pushed into Polaris initially, right? Like everything is pulled from the remote. Now there is one layer beyond that, which is in a migration scenario, you might want to proactively pull everything, right? And not just the things that your requests happen to do. And actually, that's an excellent question. I know I hinted at this. We didn't have. I didn't want to take up the time preemptively talking about this, but there is a relationship between federation and migration, which is to say, what you can do is start to have this architecture that's able to contain these pass-through facades, and maybe be able to do something like if there's logic that knows how to do caching with cache invalidation. There's recent work that adds this idea of table freshness aware table loading, where you can pass in an e tag to determine whether or not like the remote won't have to load the file if you already have the latest version. So there's little tricks, technical tricks, which you can do to make caching efficient. And then once you have that kind of protocol, you can actually build a whole migration layer on top of that, because you could say, okay, let's have the migration layer go discover all the objects, right? And then for all the objects, you'll store the current known versions, and you'll need some kind of cooperative protocol, of course, if you're going to do a migration. But ultimately, the idea would be that it's almost like you could have an rsync kind of semantic, where you say, look, here's my local, here's my remote. I want to make sure that they're exactly the same. And under the hood, things will have to exchange hashes and version numbers and things like that, just to figure out how to do it. But that can be built on top. So that would come later. Okay. Yeah, so feel free to ping me if you want to chat more, ping me on Slack or anything as well. Always happy to talk more.
Take over the spot.
Yes. Bye. No. Does that work? Oh. I actually don't know how to share my slideshow. Okay. Is that good? Okay.
We are sharing.
I think so, yeah.
Yeah.
Cool. Hello, guys. Last talk of the night. Thanks for being here. My name is Kevin. I'm one of the co-hosts for the meetup here in Seattle. And yeah, I'm here to talk about Iceberg and Delta, collaborating across the table formats. First of all, I just want to thank everyone for being here on a random Thursday. Great turnout, as always. And thank you to all the people who are sponsoring and helping with the meetup. Thanks to Microsoft for getting the space and the food and everything. Really awesome to have the space here. Yeah, this is my talk. Let's go. There's a live demo too. I'm going to speed up this because we're getting kicked out at 7:30. So
Everything will be available online afterwards, the talks, the recordings, the code, so you can check it out afterwards. Okay, a little bit about me. I'm an Iceberg committer, open source contributor. Used to work at Stripe on data platforms, especially with Iceberg. I grew up in New York. I went to Northeastern in Boston, and I'm here in Seattle now. What we're going to talk about, a little bit about Iceberg. Probably already know. The previous talks have explained really good for both Iceberg and Delta. We're going to talk about some of the similarities. Gonna have some takeaways from the talk, a live demo, and a Q&A. And just a disclaimer, I don't know that much about Delta. This is like everything I learned in like a few days' time. So, you know, if there's something that I misspoke, let me know. Cool. So, you know, you're already seen this like a million times. Like no Iceberg talk is a real talk without this diagram. You got the catalog, the metadata, the data, right? And then snapshot, manifest list, manifest file. I think the biggest thing to note from this is that there's a clear separation between data files and metadata. So the whole point is that you have some metadata about your data, which then you can, you know, it's an abstraction layer that you can work through, right? And the reason why this architecture came to be is, you know, if you have a lot of data, right, like petabytes of data, and you need a way to efficiently go look up, sort, do anything with it, you kind of need some extra data about your data, which is the metadata part. And then for Iceberg, of course, there's this whole catalog layer that you just heard about. Great. Delta, kind of the same thing, which is the theme of this talk, actually. So for Delta, you have a directory path, which is either like, you know, on object store or on your local disk. You can think of it as a folder. It's a directory structure. Inside, there's a Delta log folder, subfolder, where it hosts all of the metadata. They're called Delta log files. And there's checkpoints, that's extra information. And then there's your data file, right? So the whole point is still, you have a lot of data. You need some data about your data. That's the metadata. And then the access is through, you know, whatever represents your entire data set. For Iceberg, it was the catalog, right? I say, here's my catalog. My catalog knows what this table is. Technically, there's a metadata JSON that points to the state of the table. That's what like you get all of the data from. Here, same thing. You say, this is where my table is. It looks into the Delta log. It reads all the metadata and said, these are all my files. Very simple. And yeah, thanks. I was trying to find an equivalent diagram. Couldn't find one until I found Danny's blog from 2023. So thank you to Danny. Okay, so similarities. Already talked about table layout, metadata, data, right? That's kind of the whole point here is that you have a lot of data. You have some metadata about your data. We're going to talk about engine supports. We're going to talk about read path, write path, like generally what you do with the table and with the data. And then we're going to talk about the metadata themselves that makes up all of the magic that we talk about. Okay, great. So, you know, Spark is the thing that comes up. It's like the primary way to interact with this, right? And for table formats, what that means is you just read it and write, and you say, read Iceberg, write Iceberg, read Delta, write Delta, and you just give in the beginning of the file or like what represents as a table. Very simple. And the story is, it's the same thing for Trino, all the engines that you see, right? There's a concept of a table, whatever that means, for your engine, and then you either read to it or you write to it. That's the thing. It's all the same. Okay, let's look at the read path, right? As I alluded, if I have a Delta table, what I do is I give it the root directory, right? The root directory says, this is where my table is, right? In S3, it says, you know, you can come up with your own structure, right? It's like S3 warehouse namespace table. Everything under the table has both my metadata and my data, right? Iceberg, a little bit different. There's one more layer of indirection, which is the catalog. Catalog tells you, instead of like providing a subfolder that says like, here's my data and metadata as a table, it says, here's a key value lookup. You say, my table foo bar is right here, and here's the metadata JSON, and then the engine goes and just like fetches everything else, gets the data, gets the metadata, read, write, both doing it. And then the kind of interesting part is that while looking into both of the projects, there's a lot of similarities. One thing is, Iceberg has this concept of like file system tables, or like the Hadoop catalog is what people call it, which is like just a catalog, quote unquote, right? Because usually you think of catalog, it's like the Hive Metastore, Polaris. Like these are things that runs with active runtime as a service. But Iceberg has this concept of Hadoop catalog, which is my catalog is on disk, right? I just go, I provide a path to it. It goes, it says, I'm going to look up your metadata JSON. There's a couple ways to do that. And it's part of the spec, not really recommended, but it is there, right? The concept is still there. I give it where my folder is, and it reads all the files, the data and metadata in there. What's interesting is that a lot of the end users, because they don't want to deal with the catalogs and having a runtime, comes up with like clever tricks. So in DuckDB right now, the extension for DuckDB and Iceberg actually has a metadata guessing functionality. And if you are in the Iceberg community, it's kind of frowned upon to do this because XYZ, a lot of reasons. But if you're an end user, it just works, right? Like I say my table is in bucket this, DuckDB read that, and it just works. So for some people, it just works. And then, Iceberg also has absolute path as of right now. So like everything is absolute path addressable, which means if I'm on S3, the bucket name and the metadata and the data file is all encoded in the metadata itself. And the metadata is supposed to be immutable, right? Like you're not supposed to go change it. It's supposed to be like only one version, you write it and you never touch it. Which is kind of a problem, right? Because if I want to move from bucket A to bucket B, all my metadata is now wrong. Or if I want to move from like cloud A to cloud B, everything's messed up because, it's like they have different protocol names, like S3 versus like GCS or something like that. But in the Iceberg community, there's this concept of like relative path. Let's support relative path inside the spec itself. It's still, there's a proposal of, I haven't checked yet, I think it's active, but the idea is Delta's already doing this, right? There's something that the Iceberg community wants, and they're all kind of going the same direction. And then, through the read, Delta itself also has a catalog, Unity catalog. I can go to Unity, connect to Unity, it's a runtime, and say, hey, give me a table, foobar, and it gives you the table, which gives you the directory, and then you just read it. So yeah, there's a lot of similarities, a lot that the projects are converging. Okay, what about writes? Okay, both projects use MVCC, which is multi-version concurrency control. I double checked that on the Delta side. I know Iceberg does for sure. I double checked that on the Delta side just to make sure I'm not misrepresenting it.
It's version 1, Delta, version 2.
Okay, there is some caveat. I think something about version 1 and 2.
Version 1 is not catalog aware.
Okay, version 1 of Delta is not catalog aware. Okay, OpenAI didn't know that. Claude also didn't know that. But okay, I double checked. But yeah, the whole thing is, Delta. When I write my data file to like object store, and then I say, okay, now I want to commit all my data to the table itself, which means I have to write my metadata, which is the transaction log, right? So I can append to the transaction log in a append-only manner. I say, here's my updated table state, right? I added some files, I removed some files, and probably a lot of other operations that you can do. But the whole point is, when you have multiple writers, the first one wins, or the fastest one wins, right? And then everyone else has to retry. And Iceberg has the same similar functionality. This is done through the catalog layer itself. The rest, the Iceberg catalog, all the different limitations, the Iceberg REST catalog protocol, they all support this concept of like MVCC and the first writer wins, right? What's interesting is that, the Delta project has this, or is creating this concept of coordinated commits, which is in Delta Lake 4.0, which looks like a catalog and a commit protocol that says, sorry?
We're moving to version 2,
Version 2 of
MVC.
MVC.
Yeah, the Delta is going to adopt version 2 of MVC, so it'll be catalog aware.
Yes.
Yes.
So that's the whole point, is that
Yes.
Delta is becoming catalog aware, just like Iceberg, right? There's this idea of not only do I commit to my object store, my metadata, I'm letting another service know that something has changed, right? Same thing, Iceberg's been doing this with the catalogs, with the Iceberg REST catalog spec. And then, what I talked about with the file system table, technically, I can update my Iceberg table just with the object store and not with any catalog. Not recommended. There's a lot of reasons why. You can read about it on the internet, but it's possible. If I have a single writer, and I know I have a single writer, and I know only one process is doing it, then yeah, I can just commit to the cloud and read from the cloud and everything works. Okay, so metadata. What are these metadatas? Okay, they track data files. There's some delete files too. There's like data files too. They track the table state. So, I have some data around in my cloud bucket. I need to know what the schemas are, what the partitioning is, what the properties are. So these are all kind of a layer of abstraction above my data itself, right? This is where the table formats, the level of abstraction allows these formats to provide extra functionality, right? I can provide a schema that says everything under this table is schema aware and is compatible with the schema. I can provide a partition that says, my 3 terabytes of file is partitioned in this way so that if I'm looking at, a single day or a single partition, I can skip like 99% of it, right? So these are all reasons why like table formats are a lot better than just regular files. And then, you have history, right? How many times I commit. There's branching functionalities, at least in Iceberg, in Delta. You can have like additional stats, right? Things that helps you prune that read a lot more. I can say that, my table is sorted. My table, I can add a Bloom filter in the table or a column. I can add an index to it. So it's just different ways of adding more and more metadata about your data. And this is all done through the table format layer, right? And this is the same thing for both Iceberg and Delta. Okay, so very fast, takeaway. Like I said, table formats, just metadata over data. Very simple. There's a lot of diagrams, but it's just metadata over data. Depending, like the design principles and the design decisions are for different projects are all based off of, different ways to represent that, right? Like Delta has Delta log, JSON files. Iceberg has snapshot, manifest list, manifest files, and like JSON, Avro, all the different stuff. But at the end of the day, to an end user or to, people who work on this too, it's just metadata over data. And yeah, to end user, you look at Spark, it says, here's my table, read the table, write the table. Like as long as I get like an entry into the table, it just works, right? So all of this stuff is abstracted away. Yeah, there's some difference in design decisions that just because people come from different like contexts and scenarios. And I guess this is more of an opinion than a takeaway, but I think unification is inevitable, but in different layers. Part of the theme of this meetup was interoperability. You see it with Xtable, with translating between different table formats. You see it with Polaris, with, how do we make sure the catalogs all talk to each other? And then, there's Delta Uniform, universal format, which just says Delta Lake, Iceberg Hootie all consist of Parquet files and a metadata layer. And I think during the press conference for Uniform, the kind of slogan was that, metadata is a very, very, very small percentage of your actual data, right? So if I have petabytes of data, my metadata is a fraction of that, like a 1% of that, hopefully, if you keep it right. Right, so it's a lot easier to work with metadata about your data files than with the actual data itself, because that level of abstraction gives you extra information to do the things that you want to do. Okay, so I hope we're still good on time. I have a live demo. So one of the issues with Iceberg table, or not an issue, but something that comes up a lot is, how do I compact my Iceberg table, right? And the traditional way is you spin up a Spark engine. Spark has procedures for data file compaction, and we're going to do something different. We're going to use the Delta library to compact Iceberg tables. Kind of cool. Okay, first of all, what is compaction? Someone? No one? Okay, so I have some data files. I have a lot of data files, right? And they're in different shapes or forms. I want it to be in a form that I would like. So a very common problem is I have a lot of small files, right? I have 1,000,000 1 megabyte files, right? For Spark, what that means is I have to read 1,000,000 files, right? I have to open one file, or I can parallelize, but I still have to open 1,000,000 files, or I can just open 1,000,000 megabyte file, whatever that is, right? But the recommended is 512 megabytes. So what I want to do is I have a lot of small files. I want it to be neatly packed into 512 megabytes so that engines can read it optimally. So that's the compaction problem, at least one part of the compaction problem. Let's get to the live demo. Hopefully this works. And yeah, so this Jupyter notebook is on Gist, so you can run it yourself if you want. We're using Python, so the only dependency is the Iceberg library and the Delta Lake library. And we're releasing 0.9.0. I'm using the RC3 as a way to show it, but try it out yourself. Okay, so some notes here. We're compacting Iceberg table with Delta RS. I'll get to Delta RS later. There's a lot of interesting things that they're doing in that library too. We're going to generate some Parquet files in this as a way to demonstrate just random files. I wanted to generate TPCH, but there's some weird things going on with that. So I ended up just generating random strings or numbers. We're going to create an Iceberg table from those Parquet files. And then we're going to create a Delta table from the same Parquet files. And then the Delta library itself has a compaction function, which just takes some files and gives you back some files that's neatly compacted. And then we're going to replace it in Iceberg. So the point is, if you have an Iceberg table, from an end user perspective, add a table with 10 files, and then I call this compact function. Now my table state is actually just 2 files. The 2 of the same data, but 2 files that's neatly compacted. Okay, let's do this. So I'm going to install a bunch of stuff. This is all on Jupyter, by the way. It's running locally. You're going to import a bunch of stuff too. So one of the neat tricks for the Iceberg library and also the Delta library is that it doesn't necessarily have to work on object store, which is super cool because one, it works locally on my machine. It's just a local file system. 2, I don't need to spin up a Docker container, which it's not difficult, but it's still more infrastructure to spin up. But this is essentially there's a local directory called warehouse, and I'm gonna remove everything there, recreate it, and then see that there's nothing in there. Okay. And what I'm gonna do is this actually uses DuckDB. It generates Parquet files in ZSTD compression. I set some random, not random, but I set the row group size and row group per file to these specific amounts because I want to get 10 files with 100K records each. So essentially what this is doing, it's generating a number from 1 to 100 to 1 million. And then I'm going to partition those into 10 files using DuckDB, which is a great tool. So we're going to do that live, and it's very fast. And then I'm going to get those tables. Okay, so this is actually in my machine. I removed everything before. We just generated 10 Parquet files. I'm gonna run the tree, so you know I'm not lying. There's 10 Parquet files over there. Okay, great. So imagine this as your S3 bucket, whatever object store you use, but right now it's just my local machine, right? What I'm gonna do is I'm going to go into Iceberg land, create a catalog or connect to a catalog, create an Iceberg table, and then add those files to my Iceberg table. So then I can use them. I can use them and read them, right? And to do that, I'm using the Iceberg library. So, this just adds all 10 files. And to keep me honest, I'm gonna do a scan and a count just to make sure that we have 1,000,000 records. So what this is doing is we have the catalog, you load the table as an Iceberg table, and then I do a scan and a count. And then I can do an inspect, and it tells me all the files that's in my Iceberg table. So this directly goes through all of your metadata, Iceberg metadata, and say, give me all of the data files that you're tracking. And it's right here. And the interesting thing is, you saw a lot in the diagram, but this is the structure of the directory that's on your object store, right? The same thing as you saw before. This is my base bucket. Here are my data files. This is my metadata, right? It has the metadata JSON, which is, if you go back to the diagram, it's the top part. It has your manifest list. It has your manifest file. And these are all tracking the data files. So I just recreated a whole Iceberg table on my local machine. And this is the fun part. Okay, we're gonna take what we have and we're gonna create a Delta table out of it. You kind of already seen that with Xtable, right? What does it mean to create a Delta table out of it? Well, it just creates a Delta log for you, right? I still have my data files. I have an extra metadata, Delta metadata, that's a Delta log file. And we're gonna actually take a look at what's in there. Okay, there's a lot of stuff in here, but the interesting part is, see these statements? This is saying, I've added this file, right? And there are 10 of these. So this is what the metadata is tracking. It's tracking what data files do I have, right? This is saying, as part of my Delta table, I've added 10 data files, right? It's on here in the JSON. Great, and then I can use the Delta library. I can load it up as a Delta table, read it as a Delta table, and also find out what the data files it's tracking, right? So, 1,000,000 records tracking, these are, I should sort them, but this is 10 files that we created. And then the interesting part is, because that was the read operation, nothing's really changed, right? Like my warehouse is still the same warehouse. Okay, so fun part. Now that I loaded up as a Delta table, Delta, the library itself, comes with a compaction function. So what it does is, once you have a Delta table, you can call optimize, you can call compact, and then you give it a target size, right? So as I said, we want one or multiple 512 MB files, and these are optimally sized, right? So what I can do is, now that I have it as a Delta table, that was pretty fast. I mean, it wasn't that many files, but this is using Rust under the hood, super fast, even on my local laptop. I tried it with TPCH data, lightning fast. And look what it gives us, right? It says, here are some files that are added. Here's some files that are deleted. Gives me some stats. Great, right? I can go back to my Delta table, because presumably, Delta state change, right? I just compacted the files. It went from, 10 files to probably one. Yeah, just one file, right? So still the same number of records. And, we can go further and say that they're the same actual data records, but I didn't want to do that. It should be the same data. And now Delta, instead of tracking all those 10 files, is tracking this one big file that is just compacted. And we can list directory again. Great. So what happened here and how is it different? Delta has a zero.json. So it's a new state. It's a new metadata state, right? And Delta also wrote this new data file that it's now tracking. And we can look at the new metadata that Delta has, right? It says, okay, we removed some of your files, right? All 10 of your files. And then there's an add operation somewhere in there. So we added this one file. That's what Delta's saying, right? And then I go back to Iceberg land. Iceberg, because it has its own set of metadata that's tracking the data files, hasn't changed at all, right? It's still tracking the old 10 data files. Okay, so what I want to do is, I know the result of my compaction. I just need to shimmy it in and make sure that my Iceberg table now only tracks that one data file, right? So what I do here, and it's a little bit of a hack because it's really supposed to be like a replace operation in Iceberg, but I'm going to do delete and add as like two separate operations, but it's in the same transaction. So it should all fail or it should all pass, right? Okay, great. And then I'm going to count the Iceberg table again. Still 1 million files, 1 million records. And now Iceberg is tracking the new file, right? So what I did is I just replaced whatever Iceberg is tracking to the new data file. And that's compaction, because from Iceberg's perspective, we switch from 10 data files to one resulting data file, and it's compacted. And yeah, and Iceberg created some more metadata to track the new state, blah, blah, blah. But yeah, that's all it is to compaction. So, if we really want to implement this in the Iceberg library, we'll do like we'll add like a compact function, right? We probably don't want to pull in Delta Lake library as part of like Iceberg's official library, but because Delta is written in Rust, we can pull up some of the dependencies and expose them in Python. But yeah, this is compaction. And I added some resources to the bottom. That's the demo. Okay, what time is it? Okay, we're still good on time, I hope. Okay, so I was hoping someone's gonna ask about deletes. Because Iceberg doesn't only have data file, it has delete files as well, which tracks like records that are deleted within the Iceberg table. Right, what do we do with that? Because it's represented differently in Delta. How do you like make sure that they're like when I'm compacting, I'm just not like dropping records, right? Where I'm like, it's not the same amount of records. The good thing is, Delta has this concept of deletion vectors, and that's coming in Iceberg v3. So it's this whole convergence story of things that are good happening in one table format is coming to another table format. So, when we're in V3, if you have deletion, you can convert everything to DBs. Delta itself will understand the DBs. Compaction will work without any manual configuration or manual intervention, and everything works. Okay, so just a little slide about the future. I think everything is going to build on like reusable components, because at the end of the day, the things that the functionality that you're doing will be the same no matter which table format you want. Like maybe some of the like the design decisions and some of the like optimizations are different, but everyone is going to go to a cloud and get some files, right? There's this Apache project called Apache OpenDAO, which is open data access layer, right? It just says, I'll figure out all the ways to reach out to a file system. You don't have to worry about it. It works for everything, right? And then yeah, Open Lakehouse. So I think there's going to be more and more universal components that works across every table format, maybe even the catalogs. And the whole idea is, maybe we can build everything in Rust, Lakehouse RS. Someone else came up with that term. Danny came up with that term. And the whole idea is, if we were to write everything in Rust, all the functionalities, all the features in Rust, and expose them as bindings in either Python or other languages, then everyone wins, right? Like the compaction functionality is written in Delta RS. It's a Rust binding that it's exposed through Python. I can pull that into the Iceberg Rust library, expose the Iceberg Rust library to Iceberg Python. It's the same function. I'm just moving it around. And some references. That's it. Thank you for your time. Questions? Maybe like one or two, because we're like very low on time. Going once. Twice. Cool. Thanks everyone for being here.
Hey, before you all leave, you want to say $5? No, I'm just kidding. We wanted a group photograph, so if you don't mind, we often we can just kind of, somewhere, I hope this is okay, but we really want to, you know, motivate the community also, and I think this is one of the, this is all right. Could I ask maybe just for a quick minute, walk us over the screen and, turn off, we can take it.
Turn off the light.
Thank you. No, you stay where you are. The cameraman is gonna stand on the chair.
No, cameraman.
We am the resident giant, so I'll.
Is there a good background we can set for this?
Oh,